Now that we've discussed the law of signs, let's discuss what we call the ambiguous case. An ambiguous case is when we are given two sides and an angle of an oblique triangle. So if we were to look at this particular oblique triangle here, suppose we were given the length of this side here, and then suppose we were given the length of, let's say, I'm just choosing arbitrarily, this other side. It can be any two sides of a triangle. But what we're also given then is an angle, and not just any angle, but an angle that is opposite one of these two sides. So for example, suppose we were given this angle here because it is opposite this side, or we were given this angle here because it is opposite this side. So as long as the angle that's given to us is not the included angle, meaning not this angle here, right? Not this one, because that is an angle that is in between those two sides. It's what we call the included angle. It's included in those two sides. As long as we're not given that one, then we have what we call an SSA case. And an SSA case is always ambiguous because there are three distinct possibilities or three outcomes that we may have given the lengths of the two sides and the measurement of the angle. And what we could have is the following three outcomes. We could have no possible triangle existing, meaning it's impossible for us to form a triangle from the two sides and the angle that are given to us. We could have exactly one triangle existing, or it's possible that we could actually form two distinct triangles from one another, or two triangles exist. So we could actually form two different triangles from the sides and angle that are given to us. And oftentimes students will ask, well, how is that possible? How is it possible that we could actually have two different triangles from what is given? So I want to show you this scenario here. Suppose what I have listed right now, side A, side B, and angle B is the given information. We have two sides and an opposite angle. This is an SSA case. Now, the reason why we could have two possible triangles from this is, look, we could have this possible triangle here, but what we could also have as a possibility, and let me just kind of do this, is this side length B here that is given to us. That length is locked in place. We can't change the length of its side. But what we could possibly do, and if you want to kind of imagine that this side could actually be rotated over, almost kind of like as if it were a door on a hinge. And what you could have is something that looks like this. And let me actually just change that style so so it matches up a little bit better with what we have. So you can kind of imagine that this side length here, B, could rotate over, and this is not exact, but as it rotates over, the exact place where it could meet the possible angle, the side that would be formed from angle B, is another option. So we actually have, this would be B sub 2. So, well, I should say, excuse me, I should keep it as B. I apologize. So you have that side length B, and that length is not going to change. It is locked in place, but the position of B could change. And the reason for that is because this angle that we have here, angle C, which let me just draw out here, angle C, this could be two different angles. It could be this entire angle here, or it could be a smaller angle there. And so that angle C could change between these two possible options, keeping side B in place. Side A does not change. Angle B does not change. But what we see here are two possible angles for C. And what this would mean is that side C could be this side here, if angle C were as it is. Or, let me just change this into a different color. You could have this larger angle C, which we'll call angle C sub 2, which would then mean that this side C would be a much larger or longer opposite side. So we have this ambiguity here. And just kind of on an intuitive level, this makes sense. Because if you think about all the angles that are within a triangle, all the angles that are within a triangle are going to be between, all our angles are between 0 and 180. And if you think about all of those angles between 0 and 180, that means these angles are angles that exist within quadrant 1 or quadrant 2. And you can have an output. For example, suppose we had some angle here where the sine of this angle theta, the sine of this angle theta is equal to something like 1/2, for example, which would mean theta is equal to 30 degrees. But if I asked you what are the angles such that sine of theta is equal to 1/2, well, we know that if my angles are possibly within quadrant 1 or quadrant 2, there are actually two possible angles such that the sine of theta is equal to 1/2. We could have that angle theta here. You could also have theta could be equal to what? 150 degrees. So there is an ambiguity with sine when we're dealing with angles that are between 0 and 180. When we are, and let me actually write, just to be clear here, when we're dealing with angles from 0 to 180, we could be looking at two possible angles that could give us the same output for sine. None of the other trig functions have that ambiguity with angles between quadrant 1 and quadrant 2. If I said the cosine of theta is equal to 1/2, well, there's exactly only one angle that can do that, because as soon as we switch over to quadrant 2, now we're looking at places where cosine would be negative here. Sine, on the other hand, is positive in both quadrants 1 and 2. And so that's why there's an ambiguity when we're dealing with the law of sines. We won't see this ambiguity with the law of cosines. But with the law of sines, specifically with two sides and an opposite angle that's given to us, it is possible that there are three unique situations that could occur. And so what I want us to do is explore some of those possibilities in some of these problems and kind of work through the process of showing our work and how we would justify our answers. So let's start with this first problem. We are solving a triangle where angle A is equal to 30 degrees and side B is 10 and side A is 2 centimeters. Now, whenever I'm doing this type of problem, I'm going to kind of just arbitrarily set up a triangle. It doesn't really matter or too much about you drawing this triangle to scale, but I'm just going to kind of draw something that looks somewhat arbitrary like this. And I'm going to start with this angle here being my angle A. So there's 30 degrees. And that would mean that this opposite side A is equal to 2 centimeters. And doesn't matter where you draw B or C. I typically have B down here. And that would mean this side B is equal to 10 centimeters. Okay, so let me actually just also relabel this as A is equal to 2 centimeters here. All right, so is this actually how the triangle looks? I'm not really quite sure, and honestly, at this point, it doesn't matter too much. We're just trying to orient ourselves so we can get a sense of what we need to be solving for. So if you were given this problem, you would identify, all right, I'm given two sides and I'm given an opposite angle. So this is an SSA case. SSA means I want to use the law of sines to solve this triangle. So I'm going to set up my proportion. I'm going to say, all right, well, the sine of angle A, in this case, the sine of 30 degrees, divided by or over its opposite side, which is 2, that ratio is going to be equal to the sine of whatever angle B is, and I don't know what that is, that's what I'm hoping to solve for, over its opposite side, 10. Now, when I start solving this, so I'm going to cross multiply to try to isolate sine B. So I'm going to say sine B is equal to 10 times the sine of 30 degrees, and all of this divided by 2. Now, you could grab your calculator here if you wanted to, and you would say sine B is equal to 5 times sine 30. So 10 divided by 2 is 5 sine 30. But if we remember how to evaluate angles in our unit circle, we could hopefully see that we wouldn't really need a triangle here, or a calculator, I should say, here. We can say sine of 30 degrees is simply 1/2. So the sine of angle B is going to be equal to 5/2, or 2.5. Now, if you try to put this into your calculator right now, or using inverse trig functions, you would say angle B is equal to the arcsine of 5/2. And you could try to put this into your calculator right now, and you will likely get an error message. And you think to yourself, well, why am I getting an error message? Did I punch something in wrong? But if you really think about it, it makes complete sense to you. What the sine of what angle would ever give you a ratio that's greater than 1? And the answer is no angle. Angle B is undefined, or angle B does not exist. I should say does not exist, is undefined, right? Does not exist because there's no way that your opposite side could ever be longer than your hypotenuse, given that sine is opposite over hypotenuse. So this angle doesn't exist. And so if we kind of take a step back and think about what we're seeing here, we're saying that there is no angle B that could possibly exist that would actually make this triangle exist, given the dimensions that we were provided, with the side of angle side B being 10 centimeters and side A being only 2 centimeters. I know I didn't really draw this to scale and you wouldn't have been expected to do that. But if we actually look at, well, let me go back and kind of erase this partially. But what we actually see here is that side A was so small that it actually looks something like this if we were given that. And so what we're trying to see here is if you were to think about trying to form this triangle, is there any angle B that I could use to make this triangle exist? And you might say, oh, yeah, why don't I just go ahead and move this side so that it gets connected with that side there? But there's no way to do that while maintaining the fixed angle of 30 degrees. This triangle cannot be formed. And therefore, you would say that no such triangle exists. So on an algebraic level, anytime you get an angle that does not exist, that tells you that no possible triangle exists here. So this is an example of an SSA case where no triangle exists. Let's try another one. Now let's try a triangle where, again, I'll just kind of draw an arbitrary triangle here right now. Whoa, that's an awful triangle. It's not much better, but it'll work. So we've got a triangle here. And again, I'm not too concerned about making this look really accurate. I just want to first start and identify what type of case we're given here. We know angle A is 40 degrees. We know that side B here, so let's label this as angle B, meaning its opposite side. B is equal to 7. And side A is equal to 10 centimeters. And so we've got an SSA case here, right? We've got two sides and we're given an opposite angle. So as soon as you see that it's SSA, then you should be on high alert. You should be, all right, bracing yourself for the possibility that we have 0, 1, or 2 triangles. So it's always one of those things where I encourage students, as soon as you know that it's an SSA, you've got to be extra careful here. You want to consider those possibilities. All right, let's set up our ratio. So we would say the sine of angle A, in this case, sine of 40 degrees over its opposite side, 10, is equal to the sine of, and I'm going to choose angle B here because I know its opposite side, the sine of angle B over 7. So you're going to cross multiply here, and you would say sine B is equal to, and I'm just going to kind of skip one algebraic step, 7 times sine 40, all of this over 10. This time, if you enter in, if you say angle B is equal to the arc sine of all of this, so I'll just rewrite this. I wouldn't expect you to do that every single time, but I would write that here and enter that into your calculator. You would find that angle B is going to be approximately 26.74 degrees. And you do this just by entering that into your calculator. So 26.74 degrees. All right. So we would say, all right, if angle B is 26.74 degrees, that means, and so let me actually go ahead and box this here just to, okay, we've got that. So angle B is equal to 26.74 degrees. How would we find angle C? Well, angle C would be 180 minus the two angles that we've now found. So minus 40 degrees, which was given, minus this angle B that we just found. And so angle C right now is approximately equal to 113.259 or 26 degrees. So we've just figured out our angle C. So we've just gotten that. And so now that we've figured out angle B and angle C, all that's missing is for us to find side C. So we're going to say, all right, side C is this side over the sine of the angle we just found, so 113.26 degrees, and we want to set it equal to the ratio of the other sides. And again, you have a couple of options, but I always recommend going with the sides and angles that are given to us. So I'm going to go ahead and choose side A over sine of 40 degrees. In terms of work, that's all we need to show there. And we would say, see that pun there. Side C is approximately equal to 14.293 inches. And so we have successfully solved this triangle, and we have found all the sides and all the angles. Or have I? Because this is an ambiguous case, we want to consider the possibility that a second triangle exists. And I want to do this in a different color here. So I'm going to label this as such. Second triangle as a question. Does the second triangle exist? Well, how would we know if the second triangle exists? So listen carefully. If a second triangle exists, the way that would occur is if the supplement of the angle that we first found, the supplement of the first angle we found, leads to a valid triangle. So let me walk you through that. So the first angle that we found was angle B. If a second triangle exists, this angle B sub 2 would be the supplement of the angle B1 that we found. In other words, if this triangle exists, angle B2 would be equal to 180 minus the angle B that we found, which was 26.74 degrees. So 180 minus 26.74 degrees, if that exists, angle B2 would be approximately 153.259. And so we would say, all right, so far, we're saying that if the second triangle exists, angle B2 would be 153.259. So far, I don't see any issues. But think about it in the context of this whole triangle. We would say that we know that angle A, that is given to us, plus angle B2, that we're saying could be a possibility. Look at what we're seeing with these values. Angle A was 40 degrees. Angle B2 here is 153.259. Already we see that these two angles, the sum of these two angles, is greater than 180 degrees, which is impossible. The sum of your angles must be equal to 180. That's the triangle sum theorem. The sum of your angles must be equal to 180. Cannot be more than that. And so we're seeing that the given angle plus the other possibility for angle B, which is 153.25 or 26 degrees, already these are greater than 180. Therefore, we can say confidently that no second triangle exists. Had this angle B sub 2, the supplement of the first angle B that we found, had it been an angle that when I added to 40 degrees, that sum is less than 180, then this second triangle would exist. And you would repeat using the law of sines to figure out all the remaining sides and angles. Okay, and I'll write that. If angle A plus angle B sub 2 were less than 180, then second triangle exists. But because this is not greater, because the sum of these angles are greater than 180, we can say that no second triangle exists, and I'll box that, okay? It is super important that whenever you are solving one of these ambiguous case triangles, that you always know to check for the second triangle. Had you just gone ahead and only shown this work here, you would get at most half credit because it's so important to the understanding of SSA cases using the law of sines that you understand the possibility of a second triangle and that you know how to justify the existence of a second triangle or the lack thereof. So hopefully that this video was helpful in you understanding SSA, why there is ambiguity whenever we're dealing with an SSA case, and how to solve problems where no triangle exists, where no second triangle exists, and really you would just rinse and repeat when there are two triangles. But at least you know how to check for that.